So we'll start with the second part of our session with a talk from Reinhard Budich, who's online, about concurrency in weather and climate models. So please, Reinhard, you have the floor.
Have received the invitation and also for the possibility to be talking, although I didn't come. I'm a bit envy that I'm not there and can meet you all in person, but I decided not to fly for obvious reasons, and the train ride was a bit long for being only at the workshop, and I didn't have the time to really do it otherwise. And also we have a good system to do it hybridly, so I think we will manage. Also, I would like to thank my co-authors, Rupert and Julia, for putting together a report, which I will report about here, which is a bit unusual. I'm aware of that, but this report is an EasyWays 2 deliverable, and it is in a way not public, but still there's a lot of thoughts in there which I would like to share with you. So there's other contributors to the report as well, which I will mention in the presentation. So as I said, all this is based upon EasyWays work, and the report basically tries to tackle the topic concurrency. Back when we started drafting EasyWays, we decided basically that this topic sounds interesting. I think most people had radiation and ocean biochemistry in mind when they talked about it, but there's many physical reasons why you could run things in concurrently. Then during the activity in EasyWays 2, we somehow got stuck, but we had to write a report anyway, and we tried to do our best basically to find out why we got stuck. And this is why we have this talk today. I will try to highlight that a bit, how this happened. So, but maybe before I really jump into the problem itself, I would like to say a bit about concurrency. And I found a nice quote by a Canadian programmer named Rob Pike. He's a programmer and author. He worked on the Go application, was at Bell Labs and is now at Google. And Wikipedia quotes him basically on with the quote that concurrency is the composition of independently executing computations, and concurrency is not parallelism. Concurrency is about dealing with lots of things at once, but parallelism is about doing lots of things at once. So concurrency is about structure of your programs, and parallelism is about their execution. That's the way he sees it. And concurrency basically provides a way to structure a solution to solve a problem that may be, but is not necessarily parallelizable. So here are the quotes that you can find them in the PDF on the Google directory there as well. When we talk about the definition for concurrency in our weather and climate applications, we can decide between the computing problem itself and the type of concurrency we talk about. For instance, for ensembles, this is obviously something, some external concurrency. For model components, it's the coupling, obviously. For communications and computations, it's dealt with via I/O servers nowadays, basically. And then we talk about data structures as well, and these are done over nodes and threads. We know that basically, but there's also intercomponent functions, and that's what we also in the report call functional concurrency. And this is basically what we will talk about today. So I will provide you with an ansatz for a definition of functional concurrency, show you the findings we had about the experiences in the community with concurrency, discuss a bit the potential of functional concurrency and why it is so hard to achieve, and give you some potential solutions and an outlook. So, ansatz for a definition. The report describes it as that model components can often also be further split into finer grained components, with some of these components having the potential to run in parallel with each other. This intra-component functional parallelism is typically not exploited by model components in any depth. So examples include, but are not limited to, the atmosphere, radiation, obviously, the ocean biogeochemistry, but you can think of ice or something like that. The land normally treats rivers concurrently. So these are things which are partly have been realized, but partly have turned out to be very tricky as well. And we then searched for findings about the experiences in the community and found the examples mentioned here. Two are outside of the project, that's MPAS and Cosmo, and the other ones are ELFRIC and ICAN. I can give I can give only numbers for ICAN because the rest is confidential, and we need to be discussing these things online if we want to go into any great detail. But for the time being, it's sufficient to talk about these attempts basically. So I have from Rich Lofts at NCAR, I have details about the MPAS project. I would like to thank him a lot. I mean, he really provided a lot of detail, and we are only talking here about the intra-component task concurrency. And when he claims when he started, he had to look at cost for the execution of the tasks, at the refactoring ease, the expected acceleration, and the potential for software reviews. The first factor basically is something you can measure in realistic configuration, whereas the last things are basically soft factors, and you can only use estimates for that basically. So he had what they ended up with basically is to have the radiation in the land processes on the CPU and to port the rest to the GPU, which is interesting because basically this makes the CPU a coprocessor. And the call structure then looks something like this here. On the right-hand side, you see the CPU. On the left-hand side, the GPU. Time progresses down the slide basically, and you see how the structure of the code is now basically. It's all radiation and a bit of land basically on the CPU side. So there was lots of scrutiny and testing together with commercial partners like the weather company, IBM, NVIDIA that they did. And it was really a major attempt to do that. And that is basically the result without giving any numbers here. So what we learned, what they had to consider first, basically, if they brought the radiation to the GPU, RRTNG, which they used for that, was not ported back then when they did that, as it is now the case. Radiation was about a third of the lines of code for MPAS, so that would have been a real major task. There were many lookup tables, which are problematic, obviously, for memory access, as most of you know. And it was not clear if spreading the task to many GPUs would scale and perform at all. So basically, they left that on the CPU, and it was less of an effort to take the rest to the GPU. And then the question came up, would the radiation at the CPU be fast enough for the rest? That also depends on the ratio between the radiation and die-core time steps, basically, and the performance of CPUs and GPUs, depending on the machine and the configuration that is at hand, as well as the resources you have, basically. So, as to be expected, it really depends. First of all, if you are interested, I can refer you to Rich, or we can talk about it offline. Basically, it was tremendous work to do that. That's quite sure. And obviously, it depends on the implementation of the concurrency in the components, which is very important to remember. Okay, next thing, Cosmo. As you know, Cosmo has been the numerical weather prediction code of Meteor Swiss for some time. It was parallelized with OpenACC for the driver, the parameterizations, and the assimilation, and grid tools for the die core. So what they observed then, basically, when they threw the code at the machine, that the strong scalability saturates its 40K grid points per GPU device, and the GPUs cannot be fully occupied after that. Adding GPUs does not help. So what the idea then was basically to run the die core and the radiation every 60th time step in parallel as GPU streams, and use OpenMP and OpenACC, both in asynchronous queues. And the hypothesis was that this way the GPUs can be utilized in a way nearer to saturation. But as it turns out, the results were non-bit identical results, which makes our scientists oftentimes a bit nervous, basically. but difference should be small from theoretical considerations. So that's why they did it in the first attempt. But a full metrological evaluation was not performed. Why is that? Well, the report can be quoted, even though we observed the desired torque parallelism in the radiation scheme, we could not measure a significant improvement in performance corresponding to it. So why is that, basically? Well, too large kernels in the radiation scheme use all the resources and block other kernels. And controlling launch times for kernels would have helped, but it was not possible back then from OpenACC. So my take on this is basically it was a smart strategy, but disappointing results. They dropped the strategy for the time being. And as you see, it's again very dependent on implementation of the concurrency in the components. Next model we can discuss here a bit is the LFRIC, and this is courtesy of Rupert Ford, who helped me a lot on this as well. That's the weather and climate atmosphere code of the Met Office to come, basically. I think it's a very thorough attempt to get things considered and structured in an optimal way when you develop, while you develop the model. Obviously, the model is not yet complete, not yet with the desirable performance, but usable for prototypical case studies, as is the case here. And concurrency for components and data is treated as normal, also with DSL. You are aware of the activities of the Met Office there, and of Rupert especially. Here we look at the high-level concurrency for the slow physics within a time step, and for the radiation across this time step. Here we can look at the directed acyclic graph within the time step, and you see from time step from the beginning of the time step to the time step end, you do quite a few things, and some of them take longer if you do it time step weighted, basically. And one of the things is the slow physics, which we consider in the next slide a bit. If you blow that up, basically, then you will see that radiation is something that takes a lot of time in this, as does microphysics. So the costly parts are here, basically. And these are, therefore, you have different possibilities for concurrency to consider, depending on the complexity of the components, basically. So the approach they took is to solve out the radiation and do it parallelly to the advection and solver stuff. And by that, basically, you find out that, well, it depends on physical assumptions and cost-benefit considerations by scientists. That's very important here. So it's not enough to do that, to program that very well, but you have to really interact with scientists as well, because you have to work on the exact balance of costs for the different components. And that depends on their complexity, the frequency with which they are computed. And also, again, here, it depends on the implementation of the concurrency in the components. That's really the key point here again. Last example is for ICON. This is courtesy of many iconists, but most notably of Marco Giorgetta, Leonidas Linadakis, and Yulia Duras of DKNZ. As you know, it's our climate and weather code, our meaning MPI's climate and weather code, but it's co-owned with the German Climate Computing Center, KIT, and German Weather Service. It's comprised of land and ocean and provides ample concurrency in all dimensions, basically. What I have to mention here is that ocean biogeochemistry in the Hammock model has been ported to a concurrent ocean case, which will be described by Leonidas elsewhere, and I don't want to take the butter from his bread here. So I know that it runs very well. That's from Tatjana Ilina, who is using it in the ICON Ocean configuration also already. But we will concentrate here on the radiation in the ICON atmosphere. What Marco did in the report is really think about process splitting for slow physics in ICON atmosphere. Currently, you have all these different processes here, which could partly be done concurrently, but they are not. It's all serial. And as long as you have coarse resolution and long time steps, doing them concurrently can lead to higher tracer concentrations than the resource, which is negative concentrations, which is not very reasonable. So this is something that people tinkered around a bit with, but there are obviously other means to get good performance for the long time step stuff than go in the concurrency way, the functional concurrency way. We consider here the high resolution short time step configurations, which allow us to reduce the number of processes to radiation diffusion, and cloud microphysics. So currently we do a sequential coupling. We consider both a complete parallel coupling and a partial parallel coupling. And some remarks on the complete parallel coupling I will give on the next slide, whereas the partial parallel coupling was considered in quite some depth, although not really deep enough to be satisfying for the EasyWays 2 work package we had, basically. So parallel coupling in computing for more than one slow physics process and dynamics have not yet been done. It's a tremendous work for which sustainability is not guaranteed. A parallel coupling scheme would need 2 synchronizations, and it would have to be combined with some monitoring and regularization. So what you do basically is to distribute to the common input state to all processes computed in parallel and collect and process their output once they're done within the same time step. So scientifically, parallel coupling scheme could be developed independently. Once you have an accepted coupling scheme for a certain experiment, working with acceptable time steps, that is computing costs, such a parallel computing scheme could be developed and employed. Questionable is how sustainable this would be again. And what you do there is basically make input data and the tasks available, get work done as fast as possible, collect the results from all the resources and combine them when they're ready for the next phase of the computation. So with a completely parallelized computation of processes, distribution of resources to the tasks can be embedded in the model and might be invisible to the normal user. And dynamical process scheduling might be an option here. So this is the remarks on complete parallel computing. The partial parallel computing we did in ICANN-A basically made use of this longer radiation time step, as you probably know. This is a nice way to show that. So what really was happening then, that we developed PS-RAD in a concurrent version, but that meant basically that we had a different coupling scheme, different causality, and different results from the normal PS-RAD. So here I could show some results, but for the sake of time, I will not go into too much of a detail. Basically, the major interesting line might be the last one. PS-RAD was dropped for other reasons, so interest in working on this really ceased completely, and that was bad news. But what you can see also from the little figures I have up there is that the scientific deviation is in the range of a few percent. So it's something that is promising, but you have to have a realization of the component that is stable over time. So conclusion for ICANN, basically, for ICANN-A, more work needs to be done. Restructuring and engineering of ICANN is in full swing, as you know, in Destiny, Warm World, and other projects. For the functional concurrency aspect of it, extra funding, project funding is applied for, and we hope that we will be able to apply this here by a more modern and modular version of ICANN. So again, it's all dependent on the implementation of the concurrency in the components, and it seems to have worked for ICANN Ocean. Again, this is reported by Leonidas elsewhere. So second to last slide, the potential of functional concurrency, again, and I want to stress that, depends on the implementation of the concurrency in the components. There's no generic approach visible from our report and from what we found out so far, so it's all case and model dependent. And it's depending on the intense scientific evaluation and cooperation with those people who know about the numerics, who know about the algorithms, and who know about the machines. So it's a major task. But the potential candidate, it's one of the few potential candidates for more parallelization, we claim, but it's huge cost involved. One should be aware of that. So we have a long list of things why it is so hard. And in the interest of how much time do I have left?
5 minutes in total with questions.
Oh, okay. So I skipped this slide. You can read it out. I mean, there's many reasons why it is hard, and I will not go through them in detail. What I would like to bring across, sorry, is we do have in the report some ideas and recommendations from the report for further investigation. One of them is ESMF, the other one is DSLs, but also a combination of library code generation and modification could be thought about, and there seems to be a precursor for that at NCAR. That's basically a library between the component and the subcomponents as a subcomponent wrapper. So that seems to be an idea that is promising. As an outlook, we can say that there's technology changes on the way which might help, like for instance, the multi-instance GPU by NVIDIA for better load balancing. But there's other problems also to be considered. The proliferation of programming codes is very important in this respect, I think, and the rising heterogeneity of the architectures. Big projects plus the pressure for more parallelism might help here, because big projects might give a bit more resources to be spent on that, basically. But I think we also need to use the concept of functional concurrency to structure the problems in a way to parallelize execution of tailor-made codes of certain physical processes. And there we are back to the quote from the beginning by Rob Pike. So we have to structure the problems cleanly to parallelize the execution, basically. And with that, thanks a lot. Any questions? I'm done.
So thank you, Reinhard, for the presentation. So we have a couple of questions in the Google Docs. From Milan, are there any effort to translate the core structure tree you have been showing in the presentation directly into the code, such that the compiler knows about this tree structure and can try and experiment with the best concurrency structure automatically?
Let me have a look at I'm not sure, do you see my screen still? Otherwise,
no, we don't.
like to have a look.
We see yourself.
Good. All right. So I'll look at the question myself.
It's about the compiler managing the concurrency automatically, given the tree structure.
I'm not aware that this
actually he can do the question directly.
Milan is
sorry. So my question was really maybe it's a naive question, but the idea is just like the trees that you've drawn in the presentation. Is there any way that you can basically translate this tree into the code so that when you call a function, you also give the compiler the information of like, this is a task that should be definitely scheduled after that, but it could run in parallel to this. And so that the compiler basically starts by, let's say, the first iteration of your model or so, it just does like a random order. And then the next time it tries another one and basically just tests which one works best. And so that in the end, the compiler is basically figuring out the optimal way of doing it.
So to my understanding of the stuff, there are attempts to do and use that. If I got Rupert right, is Rupert around? Is he in the room? He could probably answer that question much better than I do. But to my understanding, there are first attempts to do that, but it's not used in any production-like or even prototypical sense of automatizing this, basically. Even automatizing putting these DAGs together is something tricky, right? So I think there's thinking about that direction, but I'm not aware of solutions really being provided for that.
I think the problem is usually because fast processes and slow process, time splitting, process splitting, and then the sequence matters in every model.
You turn on your microphone?
And then the sequence matters for every model, and no one's willing to change that sequence, and results change. And
exactly.
That's a not easy thing to do. So that's
the
problem. Otherwise,
agree,
the DAG is great.
That is exactly why I said it needs an intense collaboration between those guys really in the science part, basically, of all of this, and the guys who know about the possibilities to restructure your code, to restructure your algorithms, maybe numerics, and also know enough about the machine and their possible future to make the investment worthwhile. That's the exact problem here. So it's a very complex thing. That's it.
Go to the next one.
So the next one is easier to read. Can you elaborate on how concurrency is achieved in a fast process like radiation?
Well, I can't. I could point you to somebody who can give you more detail on that. My understanding was that slow and fast processes are both existing in PSRAD and dealt with. So I would overstretch myself to answer that in detail. But please be in touch with me. You've seen my email address, and I can point you to the right guys, basically. And then there's this last question by Reis. Is Fortran one of the reasons functional concurrency is such a big effort? I wouldn't call it Fortran. Probably if you really would be able to redo all the stuff in modern Fortran, maybe it's possible to do that. But I would more say it's legacy that is the reason for the big effort for functional concurrency. That's how I would answer that question.
Okay, we can read Brian's statement. It needs an intense effort, but if they can't utilize parallelization, they can't advance. We need to make that clear. So thanks, Brian, for this statement. Any comment? Luis, last question, please.
I mean, OpenMP does has the capability of splitting up things in tasks. So that shouldn't be very difficult, and getting it dark is as well not a real difficulty. The problem is that...
Luis, ask again.
Wait. The bigger problem is that you first need to organize the physics from a time integration point of view in a proper way. And that's something, before you even start thinking about doing this game, you should ask the domain scientists that they make their algorithms properly working. Before that, don't deal with it, because it's containing a lot of difficulty. It might increase memory footprint significantly, and it creates a lot of problems due to that. So before the physics is not really ready in a numerical sense, you shouldn't touch it.
No way to do it. Right. That's why we said.
And the other thing is
that is
radiation.
I think why Marco was insisting on having the scientific concurrency done first, basically, and then think about it. That's exactly it.
Yeah, and radiation is not a
Big
lightweight
deal,
package. It's an extremely heavy package, and it already showed that moving it out via MPI is so expensive in terms of communication and handling that it doesn't pay out for sure. In more fine-grained resolution, if you're on really coarse one, then it might help. But if it's really worth the effort, I doubt.
Nobody knows, right? Yeah. Okay. Thanks.
Also, Luis, about this OpenMP, so we find this standard dynamically to do this kind of things. Could be also an option. No, obviously we have to do some testing, but you know, for different models, different platforms, this could be also something interesting.
There's a guy at our institute who tried it.
Yeah.
just get in contact with him, and you will hear about the quality of the compiler implementations of this.
Well, let's see. Testing, yeah.
But
I mean, if we can agree upon that this is something we should, as a community, be trying to consider in more depth and with more people working on it, then this talk would have made sense, basically.
Thank you, Reinhard. We have to go to the next talk. We're 5 minutes late, but that's okay. Thank you. So next talk is Pop Studies of Earth Science Code by Jesus Labarta from BSc. So thank you, Jesus.
Now? Okay, so thank you for the opportunity of being here and telling you a little bit about, I don't know, probably you may see me as an optimist, in a sense, because all I know about weather is that today is a very nice day, and I'm trying to tell you something, I don't know, let's see if there is really something interesting or relevant or useful for you. I would like to be seen, you know the difference between an optimist and a pessimist, right? Right? The pessimist is an informed optimist. So I would like to be or to become an informed ignorant, okay? But still try to make kind of comments which are somehow resonate or somehow sensible or probably the most important thing would be complementary to what you all know and your experiences as. And I also have certainly very strong personal opinions, and probably I don't know, might be nice over a coffee, but probably there's no time at this moment. What I'm going to talk is about some of the things that we have been doing in POP, which is the Center of Excellence, where we have been doing assessments on the performance of codes, as I said, in many areas where I am totally ignorant. The idea was people could apply, and we have been doing this for 6 years. We hopefully applied for a new period, and let's see what happens or not. But ideally, people could apply to it, and we would be either at our premises or at the customer premises. We would be obtaining traces and doing analysis of the programs, trying to come out with some recommendations or some observations, and in many cases, the user with this complementary view is able to, well, at least to take into account some of these comments. And in some other cases, we have tried to do a little bit of, for example, for this, I'm supporting this task-based OpenMP. Okay, we enter into the. So we try to explore and do a little bit of proposals in there. Anyhow, what I'm going to talk today is about some of the codes, some of the analysis, and probably more about the methodology of what we have been doing, and mostly with some of codes, mostly with, I would say, IFS and NEMO mostly. Anyhow, what we do in our methodology, the first thing is try to find out about the structure of the program. What is its behavioral characteristics? In terms of metrics, that as you see here on the top, well, the top view is a timeline of MPI calls. The second view is a timeline of how long the different computations are, with a light green color representing very short, dark blue representing relatively large, and dark orange being very large. But you start seeing the structure of the behavior of the program. You are able to zoom and to find regions, as you see in the bottom. You kind of get an external perception of what the structure and the behavior of a given run in a real code. Very often, and this is a typical practice in many areas, you run the program whole execution, you say this is the speed up, the time, you run it with different core count, this is the speed up. But I have this feeling, I mean, if you go to Siberia, you take out a mammoth from the permafrost and you want to sequence the mammoth, do you put the whole mammoth in the sequencer or just try to get a little bit of tissue, a little bit, a small part of it? So what is the fundamental information which you try to be as little corrupted as possible, and there's no way to avoid corruption. So as little corrupted as possible, that lets you do some of these measurements. Essentially, as you see on the left, this analysis of a structure gives you overall understandings and perceptions of, there are regions that are very fine-grained, or there are regions where the message sizes are very small. So this is overall kind of a structure that you have to do on every sample, every core count run. And then with this analysis, you extract this small thing that you will be putting in the tissue. And on the right, we have just a direct one-to-one comparison for one iteration, for example, of one execution on different number of cores. And this happens to be NEMO. One iteration and how it goes, and the structure. Is the structure the same at different core counts or not? Are there regions that kind of get non-proportionally elongated? So a little bit of structural information, but you can also put in the same time scale, and you can do the traditional scaling studies where you say you put the speed up at different core counts, taking as reference the smaller core count that you have, or you can compute the efficiencies. This is the standard just time-based measurements, and you can say, okay, this is quite nice in this range with an efficiency of 0.85 or something like that. So it's probably okay. What we do is, beyond this single coarse grain elapsed time measurement, and also avoiding the possibility of digging down too much into the detailed analysis, which is very easy to get trapped into an analysis hole, a hole of potential where you really get very excited, but you end up not getting a global overall view. What we end up doing is we have a model which describes the performance of our application in terms of some fundamental metrics, things like load balance, What is your load balance? And quantify these things. Quantify them between 0 and 1. 0 is horrible load balance, 1 is perfect. So efficiency metrics that tell you how well is your program behaving in some of these fundamental things. On the right hand, you have the parallel related things, which is load balance. There is transfer, how relevant or how important is actual data transfer, the fact that the speed of light is not instantaneous and the speed of electrons is neither, okay? So how much is of that transfer issue affects your performance, but there's also another thing that has to do with communication, which is what are your dependencies? How much serialization do you have in your programs? On the left part, you have in orange measurements which have to do with scaling or behavior of the sequential computation parts between MPI calls. And there are things that influence things like what is your instruction scaling? Does your program have code replication or not? Are you really parallelizing well in terms of computational complexity? Is the frequency of your system behaving the same at 2 cores than at 20 than 200? And the good old times where frequency was stable and known are gone. Okay, so it's something that we have to look at. Or the other one is what's the IPC? Is how well is the code using the program? These are metrics that are very relevant, but globally, holistically, end up giving you things like in the table. Numbers like saying we have 94% of efficiency in the reference one, which so it's still not perfect, the one with 48. There are a little bit of issues. I mean, we are losing 6% of performance, but there are a few, and you see how the whole thing scales. This analysis, these tables are generated automatically out of the different samples. You put the different samples on the sequencer, and the table comes out. And what you find out is things like, well, there is parallel efficiency is probably not that good, or well, 74 is that is a little bit a matter of taste. Nevertheless, you have the computational part of the scalability is 110, so it kind of compensates. So the fact that we saw in just looking at time, you see 95 that's good. In reality, you may have things that kind of compensate each other. The behavior of systems is a very nonlinear kind of behavior. And you end up this very highly coupled effects. So the idea is that with these metrics and with some average statistic, like what is the average IPC, for example, which is not that good, but I mean there are some reasons for that. So it's kind of, this gives you in a single slide, I think, a very good description of the behavior of the application, at least the region that you have selected as focus of the analysis. Of course, you next would like to dig down into the reasons for some of these effects. Why is the load balancing going down, or why is the IPC going up? And for that is where we enter into the more detailed analysis capabilities of the tools. Now you can enter into small potential holes, let's say, and you can see the load imbalance on the left. Yeah, you can see the load imbalance where some processes take more time than others to arrive to the synchronization primitives. Or on the right, you see this, and it has been mentioned, these typical things of running couple codes, ocean and atmosphere, and well, here the metric represents the efficiency. Dark blue is you are using the cores totally efficiently. Lighter colors is that the cores are essentially idling. And it's very difficult for you and for everybody, and to really find out the setup that really is the right appropriate balance of resources between these different things. So this is the analysis stuff, and I will not have time to enter. We have other we have implementations, tangible things of approaches, how to address these imbalances in situations where you don't know beforehand what's going to happen. So that's probably another topic for another day. The idea I was commenting on causes of performance. We can look at communication analysis, things of what is the impact on the top left of very fine granularity regions, the impact of operating system noise, or which may be natural in the system or induced a little bit, but these things happen. It's important to understand them, to know them, to see and try to identify approaches to deal with them. And there have been comments about tasking, and we are kind of looking at that. And the problem of tasking is, I think it has the asynchrony and overlap potential, has the problem that current implementations have a little bit of overhead, or more than a little bit of overhead. But I think we are progressing on that. So this is the kind of things that we find. On the right, you have examples of in IFS, if you enter in the communication phases in MPI plus OpenMP things, there's first this serialization semantic that you pack, and then communicate, or vice versa. And these packings are fine-grained things. And if you parallelize with OpenMP, so it was mentioned yesterday, sweet spot is 5 or 4 cores or 3 cores. Well, these things have a little bit of influence in those performance. There are phases where the current approach of parallelization is not using efficiently all the resources. Other examples of analysis that we can do is what-if things. What would be if there was no noise? How wonderful would life be? Okay, and you have on the left examples of how wonderful would life be. The top is how life it is. Second one is how wonderful would life be if there was no noise, and by the way, transfer was instantaneous. Next one is if there was no noise by transfer to 2 microseconds of latency and 1 gigabyte per second bandwidth. And the third one is reducing bandwidth by 4. The one on the right is increasing latency by 4, and you really see that the application is really latency sensitive in this case. That was about analyzing the communication part. The communication part, yes. We also have extremely powerful analytics capabilities. I mean, it's curious how we use computers for simulating Earth and understanding Earth. We use computers, and in order to analyze computers, we just measure the time, and that's all. Okay, and we don't do a lot of analytics. And in reality, the machines have a lot of capability of generating a huge amount of data about the behavior, to which you can apply traditional analytic techniques. You can apply clustering, you can apply all those things. So you can find the structure inside those computational regions. You can characterize them and see how they change as they scale, but you can also do, in this clustering, you can kind of do tracking, the same thing that you do in tracking images. So how you track how these clusters moves in the performance space. For example, here we have at the bottom left, how they move in the computational complexity on the vertical axis and the IPC instructions per cycle in the horizontal axis. So these are evolutions and analysis and characteristics that let you identify behaviors which are, if not curious. I mean, and vertical lines for a strong scaling program is what you would expect. More cores, less work per core. Let's stay, virgencita, que me quedo como estoy. So let's stay with the same IPC, for example, okay? But these things sometimes do not happen. Sometimes, for example, when you go down there, the green on the left, the dark green region is, you see that when you start increasing the number of cores, the IPC of this region starts going worse. And when it starts going worse, you have, if you look at the other plots which show you L1 misses, L2 misses, L3 misses, you kind of end up understanding what is the situation and where it happens. And if you see on the top, the dark green region is essentially irrelevant. At the bottom is more relevant, and if you give it 100 more cores, it will be the bottleneck. Okay, so it's kind of doing analysis of what are the evolution and the potentials. And those things were at a relatively large scale. We have tracings as, I mean, you have the standard tracing, the standard tools of profs and gprofs, these kind of things. Okay, sampling. So can you combine sampling and tracing? And yes, you can. This will give you information at much finer granularity if you have long regions of computation. And you can see that within a long region that has an average performance, internally it has phases. And you can see these phases. You can see in terms of on your left, you got the bottom. You see in terms of IPC, darker, higher IPC, orange very good, but light green is bad IPC. And on the right, they show L1, L2, and L3 cache misses, and they end up being interesting numbers about or reasoning about the behavior of the code itself, but also about the behavior of the applications themselves, the architectures themselves. So, of course, you can link it to the source code and tell which function you were at every point in time, or you can represent more aggregate metrics of what is the bandwidth coming from L1, L2, L3. When are you saturating bandwidth? You have regions there where you really see that L1 or even L2 in the right-hand side is enough, and this is part of the problems with granularities that we sometimes face. But you can get a very in detail insight about the behavior of the application, but also about what to do for machines. So this is the kind of things that we have been doing in POP. You have the web page, and I mean, we are still interested in cooperating in understanding, because essentially we end up doing a little bit what Google does. Okay, Google tells you go this way or buy this thing here or something like that. They help you a little bit. By the way, they get the information about your access patterns, which they sell to somebody else. In our case, I don't sell it to somebody else, but we gain the insight to try and do some design, some impacts in our architectural thing. And I'm taking the time to tell you a little bit about this EPI project, where we are pushing and developing a processor vector, RISC-V vectors, long vectors, and if you have in the past, I mean, I think it has been close to your heart, the thing of vector architectures. And we are doing long vectors, and by the way, vectors slightly different what other people think. So vectors of vector length 256 elements, so relatively large. It's not an EEPROM of several thousands that you may be using in GPUs, but kind of the equivalent of EEPROMs of a couple of hundreds. Even if the cores themselves are not that many functional units, but this kind of allows us to do designs which are able to maximize the efficiency of the resources. And by the way, we have the chip, for example, and the chip is able to run, and we have some simple bare metal codes here, and it's able to derive performances, very nice performances for your case. Things like this thing is 40-something gigabytes per second per core on a single core at 1.4 gigahertz, which might be a good thing for codes that are memory bandwidth limited. That's the chip, which is a first version. We are doing the second one. What we have, and this is what I think if people is interested, you could contact us, and we could actually push you, offer you the possibility of really running. We have the compiler, we have the FPGA implementations where we have the latest features of the architectural design. And we are actually already doing this with some of the dwarfs, of trying to run here some of the dwarfs, and we are doing it with different codes, and essentially we get performances, as we said, sometimes, and we compare to the competitors being Intel's, being Fujitsu's, being NEC's, and try to see, well, the design point, the design decisions are somewhat different, and that's a little bit where everybody kind of positions itself, but it's I think we have a very nice infrastructure that would be worthwhile to look at and to analyze, and on which we have the same tools that we have been using. So this is what you see on the left. We have the same tools that we have with X-Try to analyze, obtain traces, obtain hardware counters. These hardware counters are also, of course, cache misses and APCs, but are also hardware counters about how well is the vector unit being used. And so these things we have the ability of doing simulations of what if our current vector length is 256. What if it was 512? What if it was 64? Okay, and it's 512 elements. Okay, our 256 is a vector length. If you compare to AVX or to other things, ours is 16,000 bits. Okay, that's the vector length that we are using. But I've seen evidences that in your codes this is potentially a good approach, and we have the ability to really have a very tight coupling process, design process of co-design process, where if we see features in the behavior, because here the yellow things are actually microscopic. Again, microscopic. These levels of details is microscopic behavior, is individual instruction levels of behavior of the program. So we have a very nice loop for doing co-design, and in your case, I think this is what we are interested, of course, with the VSC department, but Earth Sciences department, but with other people that would be interested, would really be great for us to be able to evaluate and tune and target the architectural design towards getting good performances in your codes. So this is it. This is the dates we have. It's possible to ask for access to it. It will be a little bit, we cannot serve everybody. Now we have very few systems available. We have only 3 systems available. We hope by June to have several more, up to a few tens or 40, 50, I don't know, but in that order of magnitude. And by December, we should be able to experiment with a multi-core. Having said so, I think I'm a minute out of time.
Thank you, Jesus. So we have one question from Jean-Christophe, so you can.
Hi. So I really like the idea of the top-level metrics. You know, I think that's really to have a coarse-grained view of the model. To gather the metrics in our community, we use a lot the MPI, MPMD mode, and we got quite complex execution mode, like we got the atmosphere, the ocean, we got the IO server with XIOS. And when I've tried to collect the metrics, it's actually very difficult for the tools. There's not always good support from the vendors or for the tools to collect the metrics. I don't know if there's some awareness of that. Yeah.
I don't know if Mario, what you mentioned about doing some integration of the tool. We do have today. So we have the extract, which is a package we obtains traces and for visualization, and the basic fundamental computations to compute those metrics. We do it. We have a version we call TALP. It's a version that you can is linked with your library, with your code. Is dynamically linked. Is using the LD. So it's just the LD preload, and it computes and derives these high-level metrics. Quantifies what is your load balancing, what is your communication impact, what is, and even this divides the load balancing between a component which would be within a node and across nodes. So we have tools that for us would be interesting to use them in, or try to evaluate them if you are interested. I think, and it's totally transparent for the application code, totally independent.
So do you need a special MPI library to do that?
No. It's standard. Any MPI would do.
Okay, well, you know, we are working with ECR, as you know, is multiple program, multiple data too. IFS, ECR, LPGS. We have no problem using extract and parallel. You can collect the different data per process. So at the end, the components are independent and depend on the particular MPI process or OpenMP thread, and you can collect the different metrics. So there is no problem for us.
Okay, thank you.
So yeah. No more question.
No more question in the room? Okay, so we'll go on with Willem's talk from ECMWF about the Atlas library, recent Atlas library developments for Earth system modeling. And yeah, thank you, Willem.
Hello, I'm working at ECMWF in the numerical methods team, and I'm the core developer of Atlas. So let me just briefly introduce Atlas for those that are not familiar with it. So it's an open source library that provides grids, mesh generation, parallel data structures, targeted for NWP and climate. It's a C++ library, but it has a Fortran 2008 object-oriented interface. So the intention is that it can integrate in existing Fortran models to extend them with new features. And as well as a benefit, because it's C++, you can actually interoperate with other parts or new algorithms developed in C++ and interoperate on the same data structures. It's open source. You can find it on the GitHub address, and also documentation is available on the address below. So it's an object-oriented code, and there's an extension of these possible because operators or these concepts are follow object-oriented design, where when you have one abstract concept, you can have multiple implementations, and these multiple implementations, they self-register at loading of a library. Then you can extend the library with plugins, and these plugins also can self-register concrete implementation, so you can have custom extensions. So why is it that we developed this library? Is to enable new numerical algorithms, for instance, based on unstructured meshes. For instance, the finite volume module in the IFS or FVM would not have been possible without this. So there's a support for the structured grids, but also unstructured grids, for global and regional grids, and also grids with projections. And one of the newer developments is that now we also support general Proj or Proj4 for the people that know it, projections within Atlas. There's a separation of concerns with the model developer, so the grids and mesh generation features are all part of Atlas. Parallelization, including domain decomposition, halo exchanges, is handled by Atlas. And Atlas will also provide you accelerator-aware data structures, so that synchronize between CPU and GPU, and I will tell more about that afterwards as well. Just for pre- and post-processing, there are some readily available operators for remapping, gradient computations, and spherical harmonics transforms. I don't say that you have to use these operators within a model, but they're definitely useful if you're working with standard Atlas data structures. So a typical workflow of Atlas is that you start with a named grid. For instance, the O16 grid is our operational type grids at ECMWF or the IFS, of course with high resolution. And these grids have some kind of structure. We have a custom mesh generator for this, and you get a mesh for this, and this can now be used by unstructured codes that need meshes and elements. Atlas provides halo exchanges, as I said, so partitioning with and halo building. In this case, you see some partitioner called the equal regions partitioner, which tries to split the Earth in bands, and each band is then split meridionally. On a mesh, you can discretize fields in various ways, and we have an abstraction for that called function space. For instance, you can discretize your field in nodes of the elements, or maybe in centroids. You can discretize a field with spectral coefficients. And so there's multiple ways that you can discretize a field, and the function space knows about this and also knows how to do halo exchanges on these different discretizations. So with the function space, you can then create, allocate fields, and interoperate with fields. Atlas provides a range of grid abstractions. The most basic concept of Atlas is the grid. There are two different implementations, the structured grid and unstructured grid. And then you can see that the structured grid, for instance, can be either you have a regular grid or you have a reduced grid. So in basic form, a structured grid, we consider it as a reduced grid like you see on the right in blue. So there's just like an isolatitude grid, basically. And there's some categorization that you can use. In the bottom, you see, for instance, how you would create a grid in C++ or in Fortran. And you see that there's a naming for these grids. So just by a name, it would fetch you the right grid that you can then use for mesh generation. There are some new grids which have been recently added. The first on the bottom right is the Hillpix grid. I will introduce all these grids later. Which follows in the category of a reduced grid. And then there's a new type of grid, this is the cube sphere grid. And then the Orca grids are also very new in Atlas. So Atlas also has these multiple domain decomposition strategies. On the top left, you see this equal regions domain decomposition, which I already highlighted. The top right, you have something called a matching domain decomposition. So you see this shaded background. This is the domain decomposition of an existing mesh. And you want, for instance, that the grid points of a new grid, of a different type of grid, would follow the domain decomposition of the existing one. Atlas has this as well, so that it can be useful for coupling different Earth system components models without having too much MPI communication, perhaps just halo exchanges. And then there's a checkerboard partitioner as well, and given a grid and a grid distribution which comes from the partitioner, you can feed that into a mesh generator, and out comes a standard Atlas mesh. So I mentioned that it's about new development, so I'm highlighting now what is new, and what is new is the cubed sphere grid. This has been developed by the Oliver Lomax, Merrick Rasak from the UK Met Office, and initiated by Dan Holdaway from NASA. So the reason is that at the Met Office they use cube sphere grid in Elfric model, and FE3 is also using a cubed sphere. But everybody has a slightly different definition of a cubed sphere. So you have a cube sphere where you unfold it and you have some kind of rotated T, or if you see for FE3, they have a slightly different orientation of tiles. And so there's a different projection from some kind of tiled view to the spherical view, so about how the tiles are ordered. And then another difference could be that you use equiangular or equidistant projection to do the or stretching for the to get the projection on the sphere. So another development that they've done is a specialized partitioner, so that it partitions each tile rather than the equal regions partitioner, even though the equal regions partitioner would also work with this. If you're working on a cube sphere, however, it's much more natural to have this type of partitioning. And then they also have a custom mesh generator, which is much more beneficial to use a mesh generator based on some resolution parameter, rather than treat them as an unstructured mesh, which you could already before. Then there are some cube sphere function spaces dedicated, which extend the existing node columns and cell columns function spaces, so that you can get more information on the structure in one of those grid tiles. And one of the other implementations that they've done is a dedicated cube sphere bilinear interpolation method, which takes advantage of this structure. And most existing interpolation methods that go from elements to elements or elements to points, they already work. And so you can see on the left there's an interpolation done from an octahedral Gaussian grid to a cube sphere grid with 160 divisions within each tile. And there's an arrow there that signifies that there's an interpolation between both grids possible. So from right to left, you could use this cube sphere bilinear interpolation method, and from left to right, you could use any of the other existing Atlas interpolation methods. Then we also have new support for this Hilpix grid. What does that mean? It's a hierarchical equal area isolatitude pixelation of a sphere. This is a grid defined for astronomy and mapping the space. The advantage of it is that it's every pixel is of equal area on the sphere, at least. It's hierarchical, so you can easily do some kind of grid refinements. And it's an all quadrilateral mesh when you look on the left on the sphere. However, when you unmap this or unroll this in the longitude-latitude domain, you would have at the north and south pole, you would have that these quadrilaterals turn into pentagons. However, there's an option in Atlas to split those pentagons as well in quadrilaterals in case your project or your model does not handle pentagons well and you need to work in this domain. So we intend to use this in a code called Panther, which is a p-adaptive discontinuous Galerkin dynamical core developed as part of Escape 2, or further developed at least. And this code is exactly one of those that requires an all quadrilateral mesh. Another benefit of this is that the centroids of these pixels, those are the actual grid points. They are isolatitudes, and you can therefore also use efficient spherical harmonics transforms on these meshes. We also have support for Orca grids now. So the Orca grids are I don't have to tell you, the tripolar ocean grids used in NEMO. So for that I needed to implement the Orca grid class and an Orca mesh generator class. There's a number of available grids. You see that the name is like a E Orca and then a resolution underscore and some arrangement. So the E stands for extended, it's optional. They have resolution which can be 2 degrees, 1 degree, quarter degree, or 1/12 of a degree. And then you have these T, F, U, V, W arrangements, like a grid stagger. And these specific grids, they require specific data. You can't just compute those coordinates easily. So they need to be stored somehow and fetched. And rather than using NetCDF for this, we store them in an Atlas I/O binary format, which I talk about in a second. And the reason that we have this is that now we can support Orca grids in GRIB easily, because we have, for instance, a unique identifier for these grids, and we encode just this identifier in the GRIB format, and then Mult.io is the IFS I/O server encodes that in the grip. And then Mars and product generation, it can now support these ORCA grids via grip and retrieve the data from Atlas. So Atlas is going to give these projects the necessary information to construct the grid and the mesh. There were a lot of issues getting this mesh generator working, especially when you look, for instance, on the right. There's a mesh around Antarctica which self-intersects for extended grids, and you will end up with these strange invalid elements. And if you're going to try any kind of mesh-based interpolation methods or other methods, this will for sure not work. So as part of this data, we also mark the elements that are invalid. And then you see on the left as well an example for the ORCA 2-degree grid, which is a really kind of handcrafted grid where you move points from the Sahara away and from over land to get a higher resolution over the Mediterranean Sea, and I think the Red Sea and the Caspian Sea. So this Atlas I/O binary format I just mentioned, it's a first implementation and it's experimental use just for these ORCA grids at the moment. It's a record format just like GRIB, but it's more flexible. It's not a file format, or it's more like a record or message format. It contains a header section and then a metadata section, which is a very free format. It's JSON or a YAML string, which can then describe any arbitrary data structure. In those metadata, you have references to some binary data that is described via data index section that's following. So that data index section just has a list of binary data sections afterwards. And then you have the multiple data sections possible that can contain the binary data, but this can be compressed data, and the way which compression is used is also described in the metadata. So what can you encode in this? You can encode basic types, so like double, float, integer, long, but also strings. And they are encoded within the metadata because it's not beneficial to open a whole data section just for a value. So it's encoded as a base 64 string. And then other standard C++ types are automatically encodable, like the vector or an array. There's also support for multidimensional arrays, as Atlas provides multidimensional arrays. So that requires metadata plus data. And then you can also encode arbitrary types if you just write functions for encoding and decoding. And you can write those functions really anywhere. That will just work. So you encode data from your type to just write the data in a data section. You also encode metadata, so that will be data that will go into the metadata section. And then given metadata and data, you can you can decode and get your type out again. Any compression algorithm available in ECKit can be used, and currently that is AEC, LZ4, SNAP-P, and BZIP2. If more compression algorithms would be implemented in ECKit, they can also be used. And they can be chosen independently for each data section. So you have, for instance, one specific data which is better with LZ4, another one which is better with AEC. You can choose the optimal data compression. I have to stress that this is not to be used for model output. It's not like a new format that we all have to use. Definitely not. There's grip for that. It's more used as a binary data internal to your projects, which can be portable between different architectures as well, because, for instance, NDNS is encoded and so on. So it's good for restart files or serializing data. You can send this data over a network because, as I said, it's not a file format. And so that's Atlas I/O. An example content of one of those ORCA grid files, in this case for the 1 degree ORCA grid, is shown here. So you see it's, for instance, half a megabyte about. You see the date of creation, and you see what kind of content. The formatting is a bit off here, but you see that there's the version, dimensions, the number of halos, an array of longitudes, latitudes, and flags. And all these data files for ORCA, they are publicly downloadable on some website here. And so Atlas will download those files at runtime if they're not present, or if you have them already in a cache directory or somewhere, it will just use them. And then more recent developments are about interpolation. So there's a unstructured bilinear longitude-latitude interpolation, which was implemented by Toby Searle from the UK Met Office. So it's the same bilinear interpolation in long-lat coordinates that is used in NEMO. There's a cube-sphere bilinear interpolation, I already mentioned that. Then we have structured interpolation methods that are not based on meshes, and they're like the IFS semi-Lagrangian method. So there's different orders, linear, cubic, quasi-cubic, with the optional monotonicity limiter. And they use a so-called structured columns function space, which here you see a shaded region which is at the North Pole. The red dashed line represents the pole. And you see that there's halos of 2 points created. And you see that it even goes north of the North Pole, so that when you are getting any point in between the first latitude and the North Pole, you get a full stencil, and halo exchanges will make sure that those points are getting the correct value. Then you see that there's a cubic stencil there, how that's implemented. Further, we also have gridbox average method, which is a conservative interpolation method between structured grids in longitude-latitude coordinates. There's a conservative spherical polygon method, and I will talk about this now. So this is based on an article by Kritsikis in 2015, and it works by intersecting spherical polygons from a source mesh and a target mesh, and a KD3 will find the optimal polygon. And this is already working. You see, for instance, here from a Hilpix mesh to octahedral Gaussian mesh, or one of those cubed sphere meshes. And there's a first order and second order implemented, and this will be publicly available very soon. The monotonicity is, however, not yet implemented. There's also now support for missing values by Pedro. There's also a joint interpolation and halo exchanges, so for data assimilation that is useful. And we also need to ignore invalid elements, as I just mentioned before. And here you see an example from one of the, I think, a seawater potential temperature from an Orca grid to a regular lat long grid on the right. Atlas also does spectral transforms, so you can have 2 different backends for this. One is the IFS trans library, and another one is a serialized MPI serial translocal backend, which can only do inverse transforms, but it can handle unstructured grids as an output, whereas the IFS backend is MPI parallel and can only work with global Gaussian grids, but also implements direct transforms and many more. So if you wanted to get access to this IFS backend, before you would need a special license to get access to the IFS trans library. It could be an escape license or RAPS license. But now I'm happy to announce that EC Trans is the IFS library that is now open source, and you can find it here. And this will be the latest version that will be upcoming in the new cycle of IFS. IFS itself will use the trans library EC Trans as a dependency. So that's very nice, and the EC Trans will have adaptations to GPUs, and there's already a branch publicly visible there. And Atlas will use EC Trans as well. And so now we can foster developments based on this very efficient spherical harmonics library. And let's see what the community does with data analysis and so on with this. Atlas can be extended with plugins. I'm not going to go in too much detail with this, but why would you use a plugin, for instance, is to extend existing software based on Atlas. You can develop Atlas functionality under separate version control with this, so you don't need to have a branch that needs regular maintenance. And you can just prototype maybe model-specific extensions that are not useful for the community, but you want to have them available via Atlas anyway. And for Orca is one of the Orca grids, we implemented them as a plugin. So that's one of the uses for it. We can also have Atlas on GPUs by linking two different memory spaces. There's a host storage and a device storage, and we can have, for instance, creating a host view and a device view, and there's a function on the field itself which can synchronize between host and device. So you see, for instance, in the middle on the right field, sync host device, and then you can get your device view and then launch a CUDA kernel with this device view. You can also then use them with OpenACC. So once you've updated your, so this is with Fortran, you can then use OpenACC with this data as well. You update device, and at the end you update the host again. So that's going to be very useful as well. Atlas as well will play an important role to bridge DSLs and applications. So the DSL toolchain will use Atlas underneath to access the fields and connectivity tables of unstructured meshes, and the applications can set up with Atlas as well the same fields to be used and data structures. Yes. So finally, using Atlas, some future developments is that we will use Atlas also as a backend in the IFS field API. Michael Lange may talk about this later today. So that means that Atlas fields will wrap a non-contiguous slice of an existing array. So for instance, you have an Enproma and Lev, and then Atlas field can wrap just one index and number of blocks. It can provide GPU synchronization I mentioned, but it will be a challenge to get this working with this non-contiguous slice, so we need to investigate a bit more how we're going to do that. Atlas will also be useful internally to ECMWF at least, or maybe wider community, also couple ESM components. And it will also be functioning as a cornerstone for Destination Earth developments to come. For instance, a vehicle to couple IFS with external plugins that need to get data, and IFS may provide those data via Atlas APIs. And with this, I thank you for your attention, and I'm happy to take any questions.
Yes, we do have questions. Maybe we can start with Kim.
Thank you, Willem, for the talk. I wrote the question and now realized that perhaps it's for session tomorrow, but when you mentioned the Orca grids encoded in GRIP, I was wondering if you are starting to discuss with other developers, or you have been inquired on how to use this feature to be able in other tools, in other community tools, because usually working with those GRIP files with non-ECMWF tools, it's not so easy.
Yes, so these how the GRIP will be encoded is you have this institution which is encoded in the GRIP header as well, and so this will be an ECMWF extension. So the tools to process this will probably be Mars at the moment, and so Mars should be publicly available. But you're right, this is probably something to consider with the community. Of course, Atlas is open source. This plugin will also be open source. So there can be easily tools developed that work with this, but yes, it would be good to agree on this, and maybe WMO should be involved to agree on this as well.
Okay, and then again a question on the working with Orca Grid by Uwe.
Yeah, it's I think a bit along the same lines, storing the information about Orca Grids in something new. Something related to GRIP, where the community already works with NEMO and the Orca Grid stored in that CDF file. That creates probably a bit of a reaction. So my question was if that would be the only option to work with it using this Atlas IO format.
So Atlas IO is a basic infrastructure, and the Atlas Orca plugin is using it to describe its Orca data. I don't know exactly what you're referring to, but the NetCDF is still an option for NEMO to use it. It's mostly the reason why we do it is that now we can archive the NEMO data in the same way that we archive any other of our atmospheric model data.
Yeah. Okay, I don't know if we have the time to go deep into this. It's probably because people might have already worked with a coupled model with IFS and NEMO, and then they already have the Orca description that they need for the ocean part, and then they would need another same data in a different file for the IFS. That's my question.
I'm happy to take this offline with you.
Great, thank you.
Okay, and just a final question. Are you aware of any external group, external to ECMWF, that plan to use Atlas to write or rewrite or part of their code? Or is it now just used at ECMWF? I think Météo France, right, is planning?
I think Météo France is doing some effort there. At the Met Office, especially the data simulation groups, are going to use Atlas mostly in collaboration with JCSDA for this JEDI project, which is like another kind of fork of the OOPS project at ECMWF. And then we have the Warm World project, which was mentioned by Reinhard, where Atlas could play a role in FESOM, and maybe also be investigated for use in ICON, if there would be interest for that as well. Yeah. And as well, the CSCS and the Swiss are using Atlas as an unstructured data, unstructured mesh backend for their DSL toolchain.
Okay, great. Last question by Italo?
Yes, thank you. Just a quick question about the unstructured grid, structured mesh. If you Atlas is able to handle a mesh given by the user, defined by the user with external tools. I'm referring, for example, in the case when in the ocean models based on finite element, the user is interested to refine the mesh along the coast, but different sides of the element in the open water, open ocean. So is able Atlas to handle meshes provided by the user?
Yes, there's one mesh implementation which is just called unstructured. Well, every mesh is unstructured, and it's the grid itself which you use to create the mesh, which it can also be unstructured. So that Atlas is perfectly capable to use unstructured meshes. It's just that you will probably need a dedicated mesh reader for it, so to fill in all the necessary connectivity tables and fields.
Okay, maybe one last question again. I mean, we have 15 minutes for discussion after, so it's okay if we take a little bit more time now and have less time for discussion. That should be anyway about all the presentation. So Brian wants to know why it was done, this thing of the binary format, and not use the NetCDF version anyway. And then he writes, it's about the archival. But the implication is that Mars can't archive NetCDF. Is that really true? So I guess the basic question is that about archiving NetCDF file in Mars.
I think Mars can handle, I'm not the expert, but I think Mars can archive NetCDF. I think the main driver was that we can use the I/O server from the IFS, which the multi-O, which then writes data into the FDB, which is all grip related, so that we don't need two I/O servers, which would be our IFS I/O server and then XIOS for NEMO, so we can focus just on one. And we have for our I/O server multiple backends to take advantage of, for instance, NVRAM and other things that FDB can then take advantage of. Again, I'm not the expert here. Thiago tomorrow will be much better suited to answer this. Yeah, I think that's the main reason why.
So it's because of the I/O server?
I/O server and archiving as well.
So you are already using your I/O server in NEMO, right? And not XIOS?
It's not yet operational, and but it's still in development, and I think somewhere soon this will be the case.
Okay, and a very last question about, will Atlas support the UGrid extension to NetCDF, to CF NetCDF for unstructured mesh?
So Atlas does not do any mesh reading itself. So it doesn't. Atlas itself does not support, for instance, GRIP or NetCDF. Is really just providing data structures, and you can have extra. Your model can have a mesh reader, NetCDF, that creates the Atlas mesh or via grep. Yeah.
Okay, thank you. So let's go on for the last talk of the morning by Jean-Claude André on the energy cost of the data production, data transfer, and data storing, in particular, I suppose, in CMIP6. And this is also related to the talk that Mario gave this morning.
Okay, good morning again. Yeah, as Sophie mentioned, the work I'm going to present is based on the work that Mario did. Mario's name should appear on my slide. I thought it was, but it's not. It's probably an earlier version. No, not problem. So the purpose of the work is not really to do some additional collection of numbers. It's just to try to get from those numbers a big picture of the total effort that was necessary for the European groups to produce the runs. Okay, now in this quite crowded table, you have on the left the centers which participated in the exercise, and then you have the simulated years, you have the data part, and the core hours. And for each of those types of data, you have two different things. One which corresponds to what was effectively sent to the ESGF archive, that is data or simulated years, which could be shared between all the groups, because they could go to the archive, retrieve that, and so on. But of course, a group is not sending, is performing much more computation than the one which are finally retained for feeding the ESGF archive. There are tuning runs, there are aborted runs, so the total effort really to end up with something which is worth going into the archive is much larger. So, for example, I'm not going to go into the details of the various numbers, but if you look at the column dealing with simulated years, you have a green number at the very back, at the very end, which says 270,000 simulated years produced by European groups sent to GSGF. But if you look at the red number, you see that the effort in computation was twice as large. That's something which you also can find on the last column dealing with core hours. More than 1,000 million core hours was necessary to produce the runs, while more than 2,000 million core hours were necessary to arrive to the final runs. Now, if you look at the column in the middle related to data, the number of data which are finally be sent to ESGF is much smaller than all the data which have been produced during the course of the simulations, preparatory runs, and so on. Just basically, just 20% or just below 20% have been feeding the ESGF archive. Slightly less than 8 petabytes, the green number, as compared to the 42 point something petabytes of data produced. Those data, the big difference between these two numbers may also account for data which were of scientific value, but which were not sent to ESGF. The groups which produce them kept them at the local level for their own analysis or whatever. So now, what I should say is that, and Mario mentioned that shortly this morning, not all numbers are available. Some groups didn't collect the numbers, didn't know they would have to give these numbers after the end of the exercise. So some numbers had to be reconstructed. This is what I did by just, for the groups, which provided all numbers. I computed the ratio between what was sent to GSGF and the total number, and I applied this ratio to the other groups which didn't provide all the numbers. That's crude, but I think that's the only way to proceed. There are still a few different discrepancies between numbers for different centers. I will maybe come back to that a bit later. Now, forget about the various centers, just look at the total numbers and compare them with what we could reconstruct from the CEMIP5 exercise. In CEMIP5, of course, the matrix was not developed and the numbers were very, very scarce. Some could be stored in the modeling groups, some could be found in the ESGF archive. So if you look at this I said already, if you look at the comparison between CEMIP6 and CEMIP5, you see that basically the number of simulated years which have been contributed to the ESGF archive is 3 times larger for CEMIP6 as it was for CEMIP5, and maybe up to 6 times larger, because we don't know exactly what the number of 93,000 simulated years for CEMIP5 does really means. Is that something which was the support of the archive, or is that something which was also including some preparatory runs or aborted runs? We don't know. The amount of data that you can find on the ESGF archive is basically 8 times larger for CEMIP6 than it was for CEMIP5. That's easy to do for CEMIP5. You just have to go to the ESGF archive and look at the amount of CEMIP5 data which are sitting there. The number of core hours now. Okay, something which I should mention here. Of course, this multiplication of basically 7 to 8 in data production is due to 2 facts. First of all, there have been more simulated years, contributing to more data, of course. But the resolution that was used in CEMIP6 is, of course, model resolution is, of course, much larger than CEMIP5, so which add also to data. Now, if you look at the last column concerned with core hours, basically you see that the ratio between final runs or published runs and total runs is also of the order of 50%, like it was for the simulated years. But in comparison, in comparison between 6 and 5, you see that the number of core hours has been multiplied by at least 20 and maybe up to 50, which is a very, very significant increase, corresponding to a very large part and a quite significant part to the increased resolution of the simulation. Now, from that, let's try to get an impression of the energy amount which was necessary for the exercise. Same table as the first one I showed, but now you have an extra column on the right showing the energy. The energy which appears there is in joule. Mario explained this morning in reply to a question how those numbers were computed. I should just mention here that we still have a question mark related to CMCC, the way they computed the energies. That's something we will try to sort out. But what should we learn from those numbers? The total energy amount which was used to compute this CEMIP6 exercise is 5×10 to the 13 joule, or more than 10,000 megawatt-hour. And if you want to have an idea, that you take a 1,000 megawatt power plant and you make it run for just a bit just a bit more than half a day, and then you would have all the energy necessary to produce the data. Producing the data is one thing, but the data are not sitting where they are produced, they move. Now, how to estimate the amount of energy that is necessary to move the data from one place to the other, from the groups which produce them to the groups which will use them, analyze them, and so on. So the question is quite simple. What is the energy cost of transferring data expressed, for example, in joule per gigabyte or kilowatt-hour per gigabyte? Simple question, no answer, basically. Absolutely no answer. First of all, if you look, I tried to look in the literature if you could find estimate for that. If you look at, you can find papers saying, okay, on the global internet, we have so much data transferring, and we know that the global internet is spending so much energy. If you try to make a simple ratio, you end up with something which is a few kilowatt-hour per gigabyte, once again, based on the macroscopic global internet. Now, if you go to a lab and you ask the guy who is in charge of the router how much it costs to send energy. So he said, okay, there is 1, 2, 3, 4 routers on the way between my center and some other point. Each router has a relatively limited cost, so multiply number of routers by the individual cost, and then at the end of the day, you end up with estimates which are a few watt per gigabyte. That's basically almost 2 orders of magnitude and maybe close to 3 orders of magnitude difference. That's something which is really, really very difficult. As far as I could find, I find only one paper which is really relevant for that. They really look at the way the various estimates are being done. They try to make the comparison valuable by just discarding some consumption of energy which was not included in other estimates, and so on and so on. If you believe in this publication, once again, that's the best one I could find. They estimate that in 2015 it was necessary to have to spend 60 water to push 1 gigabyte through a network. They also said that the energy consumption is probably to be decreased by a factor of 2 every second year or something of this kind. So basically what I do, I kept the number provided by Aslan, and with some updates later on, due to the fact that the 60 watt per gigabyte refers to something which applied to 2015 equipment and which might be lower presently. So there are 2 phases in transferring data. The groups are then sending all their data to the archive, and then some groups retrieve the data for analysis and so on. So as we said, we have 8 petabytes. We have 8 petabytes which have been produced. So these 8 petabytes went to ESGF. So they had to be transferred at least once for sure. And then European users downloaded part of the data. How to estimate the part that was downloaded by the European groups? You go to the ESGF side and you try to find how much data has been retrieved by European groups. That's the black part of the diagram. The rest is other groups at the international level. My best estimate, that's just an estimate, is that if you look at the 3 last year, during which data were probably exchanged for further analysis, you may say that probably 200 terabytes per month were exchanged between European groups over the network for 3 years. So 200 terabyte multiplied by 36 months makes 8 terabyte. By chance, almost the same number. Pardon me? Petabyte, sorry, petabyte. Now, 8 petabyte at 30 watt per 30 watt hour per gigabyte, because I mean the data were not produced in 2015, where the number would have been 60 watt per gigabyte, but 2 to 3 years later. So I said, okay, maybe the efficiency of the network was increased by a factor of 2. So that 8 by 30 is at 240 kilowatt. Downloading from the archive at 8 petabyte, still at a later stage. Let's assume that once again the efficiency of the devices on the network has increased by a factor of 2. You end up with 120 kilowatt. So altogether, that's say 500 kilowatt, anywhere less than 1 megawatt. There are caveats, of course. If you recall that the macroscopic analysis based on the internet was larger, then this number I ended with 500 kilowatts, or anywhere less than 1 megawatt, should be underestimated by maybe, why not, up to 2 orders of magnitude. And why is that? It's because the energy costs depend very much on the way the data are being transferred. It costs much more energy to transfer small packets in a segment than it would be to transfer a large packet at once. We just don't know the number of devices which are sitting between the place where the data are being produced to the place where they are stored and to the place they are sent for when retrieved. So that there are question marks everywhere. And on top of that, if you ask people how much is your router spending as far as energy is concerned, some can't answer the question. So question marks all over the place. Anyway, we have an estimation. Last item, which is interesting to consider, is the energy consumption for storing the data, because the data are being stored not only in the archive, but also they are kept at the individual center. This work concerning storage of data is just starting. I just have 2 estimates. Brian proposed an estimate based on the Jasmine facility, and Mario and Pierre-Antoine Bretonnière also work on the way data are being stored at BSC. And the 2 estimates are consistent, and the cost should be of something like a few megawatt per petabyte per year. A few means something between 3 and 20. Okay, once again, 1 order of magnitude difference almost between these 2 estimates. Now, if you assume that 8 petabytes are stored locally for 3 years at each of the 8 centers which are part of the CERFACS analysis, then you end up, that's an easy multiplication to do, you end up to a few hundred to a few thousand of megawatts. Now, let's recall. Production of the simulation, order of 10,000 kilowatt, 10 megawatts, if you like. Transfer of data, 1 kilowatt. Storage of data, no, I'm sorry, you should, it's not kilowatt, it's megawatt. It's not a K here. It's a M at the end. I'm really sorry for this mistake. So what remains to be done? We have a lot of work to do at the task force level, where this work is being done. We have to double check all the numbers, because the more we double check, the more modification we find. So probably that's a converging process, The more we check, the less discrepancy we will find. But I'm not sure it's a converging process. Sometimes you may find surprises. The cost of storage, as in, that's something which is probably easier to do, and all centers probably would have to look at that and say how much it costs to store such amount of data for a year. Of course, we would need to transform that into carbon footprint, which is a very the thing that is most important. But we also would have, for the IT community at large, they should really look at that problem, because I think that's something which has been not really looked at. That basically people don't know how much energy is necessary to run the routers, how many routers are on the way, what is the architecture of the network, is it an efficient network, when is it updated with newer devices, more efficient devices, and so on. That's something which has to be done on numbers and not just, estimates or rule of thumbs. This is what I wanted to show you as an overall appreciation of the total energy which is necessary for the CEMIP6 exercise. Once again, sorry for my last numbers in red, megawatt, not kilowatt.
Okay, thank you. We have a philosophical question by Joachim. I guess your question is about, yeah.
Can you keep it for you?
No. You should ask it, but then, you could also count, the energy needed to feed the people that run the simulation, or
I think
or their transport to go to their work every day, or the airplane they took to go to the HPC workshop. So let's discuss.
Sure, in the end, it's complicated, but if you want to have the total.
Can you just rephrase your question?
Yeah, the point is, I think if you just look at the individual, it's the microscopic energy use of individual routers, then you do not get the full energy footprint of the simulation. Like if you go by car from here to somewhere, you need to take account that someone had to build the motorway. So I would just advocate for just use the total energy cost of the system to be used to make the simulation, because if the system weren't there, you couldn't do the simulation. So it's even the part that idle, they're running.
No, that's more a comment than a question. In fact, I agree with you. But of course, we have to concentrate on things that we can identify exactly and try to put a number of them and make multiplications and sums. But there are other issues connected to that.
Actually, I also agree, because it doesn't mean that we are not going to measure the simulation itself. But actually, from BSc, we are trying to, as institution, as Supercomputing Center, and also to measure the different things. I think that actually, Sophie, you are doing something similar for CERFACS, no? Yes. Institution. So we have this number. It's easy to say, okay, this is for the simulation itself. But now we introduce also, we have the number for the institution, for traveling, for whatever. We have this big picture, so yes.
One additional thing that you could retrieve from this simple analysis and comparison between CEMIP5 and CEMIP6 is the rate of increase in core hours spending and so on. That's something which you could possibly extrapolate to have an idea of what will be the cost of the next CEMIP exercise. Extrapolation is not reason, but that's the only thing you can do.
Yes, I think this analysis, even if it's based on many hypotheses, I think the conclusion is that if we want to reduce the carbon footprint of our simulation, we have to think about, what we run, that's for sure, because, running extra simulation, the cost of running the simulation is high. But what I was also surprised doing this, when you gave those numbers, is that storing the data is also certainly non-negligible. And I think that, our work is to do the simulation, right? But do we really have to store all those data that nobody will never look at? And so, making an effort in storing only the useful data and cleaning the storing would save us probably a lot of, would reduce our carbon footprint. And that's probably an easier thing to do for us than to say that we should not run high resolution runs. And also, and then the last conclusion is about transferring the data we don't really know yet. So it might be important, but we don't know. But at least we know that running the simulation is something important, is costs, and storing the data. So let's clean up our storage, and that would help.
Cleaning the data is a complicated exercise because as time goes on, the groups, computers are producing more and more data. So cleaning what was there before, it's just cleaning a small part of what you are producing on the spot. So you say, okay, is it worth to make a lot of effort to clean something which really doesn't contribute to the total?
Okay, clearing, but maybe not storing. But yeah, but cleaning, but also storing only the useful things in the new simulations, right?
The new simulation, yes.
Louis?
Yeah, I'm not sure if that at the end really helps, because the amount of energy which is wasted in many places of society is much more worse, and this energy we use for what we do might be useful. So it would be much better to, instead of that we calculate in every detail what we use in terms of energy, is to enforce the European Commission to put on pressure to get rid of standby, for example, because with that you can save maybe 2 nuclear power plants in France. You can save.
Sorry, get rid of what? Get rid of what?
Standby functions in everything you can imagine, or smart homes, because they just use energy. They don't really save you. So the point is, what are you working on? And if you look in strategy papers of the oil companies in the 70s and 80s, that's exactly what they imposed on society, is try to get everybody into calculating its own carbon footprint, because then they always start comparing with the direct neighbor and the impact it has for you, and so you can split the work against wasting energy from a big point of view to a very small fine-grained thing, and it's just getting away like sand at the beach. So we should be really careful about what we do at this place and where we think about. So I'm not against having thousands of Lumis. That makes sense beside the production of the machines. So I really doubt, I'm really sorry if it makes sense to build a computing center in Barcelona, because it will never ever be able to be as power saving as the machine in Finland, or building a computing center in Bologna, because the only thing what it's doing is it's talking about prestige in a political sense, but it's not in the sense of ecological things. So it's mostly driven by politics, by oil industry, by splitting the power of the people working on things, and we are fully in this stream with this discussion. We talk where it hurts.
I'm not sure I personally agree with that. I think that, the carbon footprint of any activity is something important. We have to be at least aware of what we are doing. And of course, we're not the big players, but I think that regarding the carbon issues, there are so many small players that all small players have to do something. And of course, the big players have to do something too. But if we don't do something, if we don't talk about this at our level, we will lose completely our credibility and nothing will happen at no level.
And at least we have to know what is our share, even if it's small.
It's not the point that we shouldn't talk about. That's not what I meant. But the consequences...
we're not doing anything more than talking about it at this point.
But the consequences which we should draw, that's the point.
We have to be careful in using those numbers. But at least that's something that the community seems to be aware that the community would like to know. Now, they have the numbers. Now, what to do with the numbers, that's an additional question, and I agree with you. I mean, that's a difficult question, and we shouldn't go like les bourgeois de Calais, which are asking pardon for everything.
And it's pretty simple to get rid of most of the storage energy consumption. Put it on tape and wait a little bit longer when you retrieve.
Okay, any other final comment?
You have an additional question, no, Heis?
Oh, sorry, yes.
No? Okay.
Yeah, about the, I mean, my remark about the energy consumption of the downloads, but that was already pointed out in the presentation. It's full of unknowns, and because we experience so much also variability in bandwidth, I expect it's also very variability in energy consumption if you talk about downloads. Right? So, yeah.
Okay, I think we will finish here. I think we have to gather for the picture, right, Kim? I will let Kim. And I encourage you to read Brian's comments in the Google Doc as a conclusion.
Yeah. So, first of all, thank you. Thank you for the chairs for this third session. And now, before having lunch that will take place in the terrace, I will ask you, please, all of us, go down in front of the building to do the group photo, and then you'll be able to come here to have